Now, the modeling which we have done for the open crack modeling. So basically, this is a beam, and there is a crack. If you talk about the open crack, then this crack will remain open throughout the vibration cycle in the transverse direction. So this crack is modeled as a rotational as well as one extensional spring, and the left side of the beam is modeled as a different sub-beam. Right hand side of the beam is modeled as a different sub-beam. Both the sub-beams are connected with the one torsional and one extensional spring. This torsional spring represents the discontinuity in the rotation at this crack location, and the extensional spring will take care of discontinuity in the transverse displacement in this particular crack location. In fact, if we talk about only the rotational spring, it will lead us towards the mode 1 fracture, which is the opening mode, and the discontinuity in this rotation displacement here at the crack surface, that will be proportional to the bending moment which is applied at this section. And similarly, the extensional spring will take care about the discontinuity in the transverse displacement at this crack location, and that discontinuity in the transverse displacement will be proportional to the shear force which is acting here, and that is basically the talking about the mode 2 fracture. Obviously, mode 3 fracture we are not considering here. Out of plane molding is not considered. Furthermore, we have also found that the system's total strain energy after considering the springs, the coupling can be further neglected because the effect of shear, influence shear, in particular in the open crack, is very negligible compared to the opening mode, the first mode. So if we model it by a rotational spring, then as I told that remaining in the framework of the linear elastic fracture mechanics and without considering the crack growth also, several beautiful outputs can be taken out for the structural engineers. That is what we are seeing. So a simple linear elastic fracture mechanics theory, if we follow, this G is nothing but the flexibility, and Kt is the stiffness of this torsional spring. Once we obtain the stiffness of the torsional spring by obtaining the expression of this G, this is nothing but the flexibility. Don't confuse it by the Griffiths energy. This is just the compliance of the flexibility, and by that we will get the stiffness of the rotational spring. Once we get this, the total strain energy of the system can be obtained very easily. And I am not going into much more detail of the vibration modeling of this particular structure. It is simply the energy method has been followed, or there are various methods which have been followed, and geometric nonlinearity has been considered because nonlinearities are inherent, and by doing that we will end up by using suitable techniques we will be able to find out this eigenvalue equation. This eigenvalue equation is nonlinear because the stiffness matrix here is nonlinear, and for the open crack, as we know that there is no time dependency of the stiffness, it is quite easier to solve. Any general equation will give the solution of this equation, Newton-Raphson Runge-Kotler, by any differential equation solver will get the eigenvalue problem, we can solve it. This equation we have particularly solved by just following on iterative technique, so we will get the final response, and we will see how this cracks effects in the responses. Secondly, if we talk about the breathing crack modeling, there generally there are two models widely available. One is the bilinear crack model, where it is assumed that in one half cycle of the vibration, suppose this V is the vertical displacement of the beam, so in the upward cycle, a half cycle of the vibration, this crack will remain completely closed, so it will behave like an intact beam, and the natural frequency will be equal to the natural frequencies of the intact beam. And in the another half cycle of the vibration, this crack will remain completely open. That is what the bilinear crack modeling means, that it will remain completely open. So whatever flexibility expression we have obtained in the previous for the open crack modeling, that can be used for one half cycle of vibration, and for another half cycle of vibration it will be zeros. So by this the bilinear crack modeling can be done. If we specifically talk about the breathing crack modeling, there it is assumed that at one half cycle of vibration the crack will remain closed, the beam will be intact, then the second half of the vibrating cycle, the crack will get gradually open, okay, and it will be depending on the displacement, and this displacement basically is coming from the nonlinear equation, so it is difficult to predict. So by that the flexibility will be the open crack flexibility multiplied by the displacement, which is a function of time, by the Vmax, which is nothing but the maximum displacement at this place. So now if we convert it into stiffness, basically inverse of this, then the stiffness itself will become a function of the nonlinear displacement, which will be a function of time. So this modeling will be a bit different, and because of this the frequency which we'll get at one half of cycle will get a different frequency. In the second half of cycle where the crack is opening, there the stiffness is a time dependent parameter, so we'll get multiple frequencies, and by taking a harmonic mean of that all frequencies, we tell that the beam is vibrating with one dominant frequency, that is the dominant frequency that we'll get later on. Interestingly, we have also found when we did the force vibration test that the resonance is happening near in the neighborhood of the resonant neighborhood of the dominant frequency. So that is what we'll going to see. Talking about the experimental setup, what we generally do is we take the specimen, we prepare a notch, we put it into some cyclic loading, and if some fracture or some crack grows there, then we stop it, and then we put it in our smart shaker. Actually it's a very old figure in from our lab. Now we have a big electrodynamic shaker where we can test up to 1000 kg of load. So for the larger structure we use electrodynamic shaker for the excitation. For the smaller for the lighter specimens we use this smart shaker, which can take care of the excitation part, and excitation is given. The response is taken care by the sensors, which we generally use. For the lighter sections we use generally laser Doppler vibrometer, which is a non-contact type sensor. For heavier section we can use accelerometers, which because the mass will not impact the dynamic behavior. For the lighter section, mass of the accelerometer, because it's a contact sensor, it will impact the dynamic behavior, so we use laser Doppler vibrometer. We connect it with the data acquisition system, and then by the post-processing software we post-process the data, and we have found a very close relation between whatever modeling I have proposed and with the experiments when we did it with the simple metallic beams. So I'll just talk about some of the results which we have obtained from last 4-5 years. This is a simple cantilever beam with a crack here, and we'll be talking about the open crack, how it behaves, the behavior of the dynamics. So the crack depth is taken as A. Although this analysis is done for a functionally graded material, here there is no scope, there is no point of talking about functionally graded material in their response, because we are generally talking how the crack is behaving to the dynamics of the structure. So only one response we will see. Basically this one response is for the isotropic material. The beam parameters, everything is given here, and we have this is taken from our published article. This behavior is showing the first mode of vibrating frequency with the crack location. We can see here, as the crack location is near in the neighborhood of the fixed end, the frequency is minimum. Although it's a common understanding that if the flexibility is being induced, then the natural frequency has to be reduced, but we can see that the frequency gradually increasing when the crack location is shifting towards the free end. In fact, this free end is the moment free end, so there is no bending moment, therefore there is no discontinuity in the cross section, so there is no effect of the crack. So for the first mode, the influence is like this, that the crack influences the dynamics when it is located near in the neighborhood of the fixed end. When it moves towards the free end, the effect goes down. We also found it for different boundary conditions, and there are several factors which affect this severity of the cracks that I'll discuss in the conclusion slide what exactly happens. If we talk about the second mode also, we can see here there is a bit variation here, because we have one vibrating node here in the second mode of vibration. So if somehow the crack is situated at any of the node of the vibrating mode, then there will be no influence of the crack, obviously, because there is no displacement at all, so there is no discontinuity. Otherwise it will affect in the same manner, and same goes for the third natural frequency. Similarly, for crack depth ratios, if we increase the crack depth, then definitely the natural frequencies will reduce. Okay. For all the modes, the same behavior is obtained, and this is for the linear frequencies. Now, if we talk about some nonlinear attributes, when we model it nonlinearly, because nonlinearity is an inherent, so we cannot avoid, and we are talking now here the effect of the cracks on the nonlinear vibration behavior, and that too now we are exciting that particular beam which was having one crack with some harmonic excitation f sin omega t. This is nothing but the displacement history of a healthy beam. The black curve is for the healthy beam and the red curve is for the cracked beam, and this is a steady state response. Obviously, the amplitude we can see for the cracked beam, the amplitude is quite high compared to the uncracked beam. This figure we have obtained when we excited this system with the excitation frequency omega equals to half of the natural frequency of the system. Now, when we excite this system with another frequency, now the frequency of excitation has been changed. Now, at 0.33 of the natural frequency of the system, when we excite it, we got a super harmonic resonance here, and effect of cracks are prominent there, and we can see here that since we are exciting it with the 0.33 of the natural frequency, everywhere this effect is almost remaining same. For the crack also, only thing we are getting is the amplitude is being increased. Similar thing we observe in the phase plane plot of the same excitation frequency 0.33 from the natural frequency. This is a typical closed orbits we can find out in the phase plane portrait, and this inner orbit is showing about the crack depth 0, it means the intact beam response. Then gradually when we go out from this orbital, we are finding out when the crack is growing, the orbital response of the phase plane portrait is growing. That is because the velocity and the displacement both are growing in the same way when the crack is being, the depth is being increased. If we talk about the harmonics of this response, how the crack is affecting the harmonics, when we excite this system with one single frequency like f sin omega t, where this omega is the excitation frequency is equals to 0.33 of the natural frequency, we found that the first harmonics is dominated by crack depth ratio 0.7. When the crack depth ratio is 0.7, then this first harmonic is dominating here. 0.7 will, the crack depth 0.7 is having the maximum impact for this first order of harmonics. However, for the second, third, fourth order harmonics, there is a slight response contribution of the third order harmonics here, but this response is almost same for all the crack depths. However, if the same structure, if we are changing the excitation pattern, and if, because the random vibrations, random excitations can come in any nature. Now we know that the periodic, any periodic excitation can be written in terms of its higher order harmonics by using the Fourier series. So if we have changed this excitation pattern, and we have given it with a multi-frequency excitation, and we have changed the excitation to f sin omega t plus f sin 2 omega t with the same structure, and this omega being same as 0.33 of the natural frequency of the system, we found the response of the intact beam, that is in the black color, and the cracked beam which is of the crack depth ratio 0.7, which is in the red color. This is the time displacement history, and this is a steady state response obviously, and these are the phase plane portrait. We can easily see that from the phase plane portrait we can easily identify the cracked response compared to the intact beam response. Interestingly, if we see same structure when we excited with different frequencies, the order of the harmonics which got changed. Now if we see the first order harmonics is basically dominated by intact beam, slightly more than the cracked beam response, and we can see here slightly at somewhere at this fourth order harmonics, we have a very large dependent of this crack depth 0.07. So for the beam which is having a crack depth of 0.07, here with this excitation basically the fourth order harmonics is dominating here, very high. Similarly, we can see that fifth order harmonics also, it's dominated by the cracked beam response. So take out from here basically is the response of a cracked beam, although the crack is not growing, response of the cracked beam which is in the form of either typical notch. So we have discussed about the open cracks here, so which is in the form of a typical notch. There are various applications which can be possible, and there are various takeouts which can we can take from here, that even if the system is same, if the excitation is different, the crack is going to behave differently. The modal parameters of the structure is going to perform differently, and the steady state response which is coming from the excitation, which will be significantly different. So this is one takeout which from structural engineers can take for the structural health monitoring purpose. The second thing is the response of a breathing crack modeling in the dynamics of the beams. Now same structures we have taken, and as I told that in the breathing crack basically we talk about the dominant frequency, and how we get the dominant frequency is, since in the breathing crack as I have already showed you that the flexibility will be time dependent. For one half cycle of the vibration, the stiffness will remain constant, or it will behave like a intact beam. For another half cycle of the vibration, the flexibility will be induced, but the crack will grow gradually, and therefore the flexibility will be a time dependent term, and hence the stiffness. So since stiffness is a time dependent term, if we take different instant of times, the frequency will come different. So therefore this dominant frequency or the breathing frequency is taken as the harmonic mean of all the frequencies taken at different instant of time in one half cycle of vibration, and obviously for one half, that is pi, it will be nothing but the frequency will be the frequency of an intact beam. So when we took this, we got the dominant frequency, and interestingly we performed the forced vibration analysis with that structure, and we found that the resonance was coming in the neighborhood of this dominant frequency. Although it was just an average of that, the harmonic mean of that, but the resonance was coming in the neighborhood of this instead of in the neighborhood of any closed beam frequency or the completely open cracked beam frequency. This is the response which is showing with the crack depth how the frequency is changing for open crack model, for bilinear crack model, and for the breathing crack model. For the open crack model, the reduction in the frequency is quite high, it is very large. For bilinear crack model, the frequency is in between the breathing crack modeling, and for the breathing crack modeling it is more accurate, and it is a more accurate modeling obviously, because the crack is opening and closing in the time, and this reduction is plotted here. This is the response for, this is a time response, and this basically, this is not a steady state response, that is why it is looking a bit hazy. So this is what I had to talk about, what we can take from, even if the crack is not growing, because we assume that the engineering structure will not fail by cracking, but somehow if some crack gets developed, and we perform the online condition monitoring, online vibration testing. So if we have the vibration data from the operating structure, by seeing the shift in the response, we can clearly identify where the crack is. There are various techniques also by using this response, the identification of the crack. Basically there are two different techniques. One is the forward method which I showed, when we know the crack parameter and modeling it and getting the dynamic behavior. Another is we take the vibration response, which is more practical. We take the vibration response, and out of that we try to measure what are the crack parameters if there is any crack. So that is inverse method, and both we generally do. So this is what I wanted to tell about how the crack affect the dynamic of the beams, and there are so many things to take out for the structural engineers. More or less what we have discussed, and the key observations are reduction in the natural frequency. That is a very key fact, that whenever there is a crack or whenever there is a flaw, because of the local flexibility, the induction of the local flexibility, the natural frequency will reduce. That is a sure shot phenomena that is going to happen. Severity of the crack on the dynamic behavior varies with boundary conditions. Now, with boundary conditions means if we talk about the clamp structure, if there are some point of contraflexures, and in the point of contraflexures if the cracks are there, then there will be no effect of the cracks. If there is, if we talk about the second mode of vibration or third mode of vibration or higher mode of vibration, and if there is a vibrating node where the crack is locating, so we will not get any response from the crack, we will not get any effect of the crack on the response. So location of the crack, same. So location of the crack also matters. The effect of cracks on nonlinear dynamics is highly dependent on the excitation. We have also seen that the same structure, when it is excited with the single frequency excitation, we got a different type of response. Basically the dominance of a particular mode was happening in some particular cases for intact beam, and same was completely changed when we saw with the two frequency excitation or multi frequency excitation. When we excited with a different excitation pattern, then the crack affects the different modes differently. That is what we have seen also. And dominant frequency, this is one concept which also is a takeaway, that if there is a crack, generally crack are breathing in nature, the fatigue cracks. So the resonance which we generally, the structural engineer, we generally try to avoid, so that will be closer to the dominant frequency, not to the frequency which we get from the open crack modeling, or not to the frequency which we get from any bilinear modeling. So it is basically closer to the dominant frequency, and dominant frequency is relatively different from what we get from the open crack modeling. So that is all for this talk. Thank you. I am open to you all. Yeah, actually that we are now exploring. There is one part of research which we are now exploring, that is remaining life prediction of a structural member. So there definitely this crack growth has to be taken care. So that modeling we have not explored it. We have just started exploring that how, when the crack will grow also, because the vibration cycle, if it is going on, when it is growing, then how much time it will be there for complete failure. But in general, for the structural health monitoring, we don't allow the crack to propagate. As soon as we detect a small deviation in the vibration response, immediately the corrective actions has to be taken care. That is why we have not explored it yet, but now we are doing that theoretically, so that we can explore what will happen and how theoretically we can predict the remaining life of a structure which is under vibration. Crack has initiated, and when crack is propagating, how much time it will take. That definitely there will use the fracture theories, fracture growth theories, and that is our next task which we are going to perform. Yeah. Okay, yeah, so that actually, that study has been done. I have somehow I have not presented it here. Multiple cracks you are talking about. Yeah, so those studies have been done more or less, because the effects are going to remain same for one crack, whatever is happening, but the severity will be more. These are in different locations. So therefore, instead of showing the multiple cracks, I have shown the variation of the response with changing the locations.
Okay. Are there other questions? No? Well, then okay. I thank you.
Thank you.
Thank you.
Thank you.
Let's see, we are now ahead of the program. Let's see, we'll meet again then at 3 o'clock to be on time. Hello, 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 hello. growth in amorphous polymers, effects of loading rates. Please.
Okay, good afternoon everyone. Thank you organizers for calling me in the first Fracmeet conference. So I am Anshul Pai from Department of Mechanical Engineering, IIT Bhilai. I will be talking about the void growth in amorphous polymers, specifically effects of loading rate on growth. So first of all, regarding the amorphous polymers, I will be mostly talking in a continuum manner, no molecular level things. Okay. So if you look at amorphous polymer and if you look at the deformation behavior of it, so basically when a strip of the amorphous polymer is loaded, initially it shows an elastic response or more or less viscoelastic response. At some point of time there are shear band appears in these bands and they go to instability region, which shows a yield like behavior the way we generally see in metals. And these kind of behavior are kind of intrinsic to these polymers and they show a softening, and after that these shear bands expands throughout the length of the strip and almost at a constant rate, which actually gives large deformation to these structures. And after that, when all the polymer chains when the shear bands have spread throughout the length, basically all the polymeric chains are kind of straightened and they are aligned, and once they are straight, they can no longer stretch, and after that the fracture happens. So this is basically the overall deformation behavior of the amorphous polymers. So these are kind of advantages. They undergo large deformation. They show a yield stress which depends upon temperature, pressure and strain rate. They show strain softening, which is a kind of intrinsic behavior to that. Rate and temperature dependent hardening behavior after the softening. So some of the examples are polycarbonate, PMMA, polystyrene, etc. As far as engineering is concerned, these materials are important because they show a higher toughness, and because they are loading rate dependent, it has been observed that their toughness is also rate dependent. So they are mostly used in the impact kind of loading conditions. Okay. Now why wide growth? Because growth and coalescence of microscopic voids are generally precursor to the ductile failure in metals as well as amorphous polymers. So that's why we will look at the void growth analysis. Now before we go into the simulations of void growth, I would like to show some of the experiments which I have done way back during my PhD. So basically what we will be looking at, we have this. So this is a 3-point band specimen which is generally used for doing the fracture test. What happens? This has a pre-existing crack. It is supported at two ends, and then we apply load at the top so that the crack opens in mode 1 loading. Okay. So what you will be looking at? We will be looking at a close-up of this crack. Because these materials are transparent, nothing will be visible, but because these crack faces are there, they will be having a so let me first show the picture. Okay. So what you are seeing here, this is the crack face which is illuminating because of the light. Everything is transparent here because the material itself is transparent and the background is black. Now what you are seeing here, when the loading starts, you can see at somewhere ahead of the crack, these kind of defects start appearing. The material does not immediately fail, the specimen does not immediately fail. There is a accumulation of defect ahead of the crack, and once the defect is sufficient damage has accumulated ahead of the crack, it joins with the main crack and the fracture happens. Okay. So this is a static image of the same thing. So initially you can see this is the crack front which has no defect ahead of that. At some particular load, a small defect appears at an isolated place. Once the load increases, this defect which was initially there, it starts growing, and another defect appears at some other location which is again isolated from crack as well as from the initial defect. The same process goes on. Now both of the defects are growing and another defect appears, and with the growing time, all these defects which are appearing, they join together and form a big defect, which basically forms a big defect and ultimately it fails. So this is what happens under the static loading. The loading is applied very slowly. Now we did the same experiment at a high speed, that is impact loading. So this is what you see, again the same configuration, only thing as a camera is now looking at a different angle just to observe things. Now this is under the dynamic loading. Here also you can see this image is this phenomena is very fast. I will again show the static loading. So these images are taken at an interval of 1 microsecond. Okay, so again the same 3-point bend configuration, the only thing is that it is under the impact loading. So initially there is no defect, however you can see a small defect appearing in front of the crack, and then this defect spreads and connect with the main crack and the fracture happens. So phenomena remain more or less same, the only thing is in initial case static loading, the defect has lot of time to accumulate, whereas in dynamic it does not grow bigger, it's very soon it joins with the main crack and failure happens. Okay. So this is the phenomena which actually I analyzed during my PhD, and what we saw with the help of simulations, that the mean stress, so basically if we consider, so this defect we are seeing in more or less in a two-dimensional manner. So we don't know whether this is a void or what kind of shape it has, but since void is a kind of good assumption of any defect in the structure, so we assume that it is a void, and because mean stress or pressure is something which is responsible for generally expansion of voids. So what we looked at into the simulations, we looked at the mean stress at the location where the void is growing, or the location where the mean stress is higher. What we found that with the increase in rate, with the increase in loading rate, this mean stress which is responsible for defect initiation, that increases. So we saw a rate dependent mean stress which is responsible for defect initiation or void growth. At the same time, we also did experiments with different notch radii. So these are the different notch radii we looked at. This is larger, this is smaller than that, this is the smaller, and then there is a sharp crack which is cut through the blade. So by having different notch radius, we can basically vary the trajectory ahead of the crack. And again, when we did the similar kind of experiments, what we found that this mean stress also depends upon what kind of notch radius you are having. So basically it depends upon the trajectory also, what is there ahead of the crack. So now we found that the mean stress depends upon the loading, mean stress depends upon the trajectory conditions ahead of the crack. So this is one reason where this is one place where the void growth is important, and we have looked at it. Another place where void growth becomes important is basically the polymer blends. Polymer blends are this is an example of PC-ABS blend, which is an immiscible blend. Polycarbonate is one of the polymer, ABS is another polymer which does not mix with the polymer, and it remains there as a particle. Okay, now what happens when these polymer blends are loaded? The ABS again consists of two particles. The one is rubber particle, another is one is rubber particle, another is sand matrix. So when loading happens, this rubber particle actually cavitate at a very low load levels, and they form a hollow sphere. So now this is like a polycarbonate matrix with all voids everywhere. Okay, and these voids now govern what kind of behavior this PC-ABS blend is going to show. So again, if you want to find out if you want to derive the deformation behavior of these kind of blends, we will have to study what the void growth behavior in the polycarbonate. And these PC-ABS is again a material which can sustain very high, which shows very high toughness at higher loading rate. So this is also used at mostly in the higher loading rate configuration. So that's why the effect of loading rate should be observed on the void growth. Now, effect of trajectory under static loading has already been studied by Steinbring, but we will again look into it. He has done mostly for the small deformation. We will go look into the large deformation case. The effect of loading need to be addressed, which has not been addressed yet. So what we are going to model, we are going to look at the continuum. Now we have chosen a RVE, which is a hexagonal shaped RVE, but that can be approximated as a cylindrical RVE, and then we considered a void inside it. We will look into different configuration. Now making it a cylinder helps us in idealizing this cylinder as an axisymmetric object. So instead of doing a three-dimensional simulation, we can basically do a two-dimensional axisymmetric simulation. That is our life. Okay, and then in order to maintain a constant triaxiality, to look into the evolution of void under different kind of triaxiality value, we will be applying the stresses, remote stresses or macroscopic stresses at a constant ratio, such that we can control the loading condition and characterize what kind of parameters are required. Okay. Now, we will be looking at different parameters throughout the presentation, so I will just define it there. So, macroscopic so basically the stresses in x1 and x2 directions, the macroscopic stresses are given as average stresses in that direction, which is denoted as sigma 1 and sigma 2. Macroscopic mean stresses are given as sigma m, which is nothing but the pressure, sigma 1 plus sigma 2 plus sigma 3 by 3. Remote triaxiality, which will be defined as the ratio of mean stress to the von Mises stress, which basically defines whether the component is subjected to more hydrostatic kind of stress or it is subjected to more deviatoric kind of stress. Higher the triaxiality, higher will be the hydrostatic loading, lower the triaxiality, it will towards the distortion kind of loading. Void volume fraction, we will be looking at how the void volume is growing with respect to the overall cell volume, that is the ratio of this thing. Macroscopic effective strain is again strain, we are converting a two-dimensional strain. This is kind of similar to the von Mises stress corresponding to that. And then applied shear stress, this is something which is there for a unvoided section. We will be using it to normalize our plastic strain rates for our voids. Okay. Now, in order to simulate this model, we use a constitutive model which is given by Wu and van der Giesen 1996. It depends upon a model given by Boyce in 1998, which was a very simple model, but it can take care of almost all kinds of things: rate and temperature dependence and pressure dependent yield, strain softening, rate and temperature dependent hardening. It can take care of all these things. These are some of the calibration. The model is calibrated against the experimental data for polycarbonate, and rest of the simulation we will be doing only for the polycarbonate. This model has a problem. It can the dots here, the black dots here shows the experimental data of yield stress with respect to strain rate. What does the general behavior shows that up to a certain strain rate it follow a constant slope, and after a certain strain rate under the impact condition it follow another slope. There is a change in slope of the yield stress when at a higher rate. Now, the original model given by Wu and van der Giesen that can only capture a linear behavior at all the strain rates. So, I have modified this constitutive model so that it can capture this kind of bilinear variation of yield stress at all the strain rate, and this model I will be using for my simulations. I am not going into this into the model as of now. Now, the finite element analysis. So, this is my mesh basically. So, the nonlinear constant equation. So, basically now in order to maintain the constant triaxiality, what is basically done, we take a particular node here where we apply a uniaxial loading. Now, this node and this node of the cell is connected with some kind of nonlinear constraint which has been defined by Faleskog in 1998. These constraints basically convert this uniaxial loading into a biaxial loading or some loading which can maintain the constant stress ratio on this cell, which in order maintains a constant triaxiality. Okay. So, basically this cell will be subjected to a loading which will maintain the constant triaxiality throughout the loading. Displacement control loading. Displacement of node M governs the deformation of the cell. Now, we will be considering different void size, one is small, one medium and one large. Large voids can be so basically this can be considered as a periodic media where this cell is where voids are distributed in a medium. Okay, this is like a periodic boundary condition. We will be considering different triaxiality, 1 by 3 which corresponds to a uniaxial loading, 2 by 3 corresponds to a biaxial loading, 3, 1, 2, 3 these are the triaxiality which you will generally see ahead of the crack or the notches. These are higher triaxialities. Applied strain rates, we will be considering a range of strain rates varying from quasi-static to dynamic. We have performed both two simulations. One is static simulation, dynamic simulations. Now, when we say static simulations, even they don't look into consider the inertia effects. Okay, so when we talk about dynamic effects, two kind of effects are coming into picture. One is the effect which is which is coming from the material rate dependence. If your material is strain rate dependent, it will show a higher response at the higher rates. In addition to that, when you consider dynamic conditions, inertia effects also come into pictures. So in general, if you are running a dynamic simulations, both rate effects as well as inertia effects will contribute into the simulation. But in order to quantify them separately, once we run a static simulation where inertia effects are off, in dynamic simulation inertia effects are on, so that we can kind of quantify both the effects. Now let us first look at the results of a static simulation. So these are the three responses of remote mean stress versus the void volume fraction. So we are basically looking at how the mean stress is varying with respect to when void is growing. So this is normalized void volume fraction with the initial size. Okay, we see basically at all the strain rates we see similar kind of response. With the varying triaxicity, what we see that the void volume fraction, the void growth increases with increase in triaxicity. The void volume increases more and more as the triaxicity is higher. If you see a response at some triaxicity, what happens initially, the void grows very slowly. Okay, after this linear part actually corresponds to a elastic growth of the void. Then suddenly there is a peak stress, after which the void, so this is a maximum stress, after which it shows an instability. So void grows suddenly to a larger size. For example, if I consider this green color curve, up to this particular point the void grows very slowly, the F changes almost negligibly. After that, as soon as it reaches this stress, the void will suddenly grow to this particular size, and again it will stop increasing. That means, so this is given for the smallest void size which I have considered. Okay, so void grows very small, then it suddenly becomes very large, and again then the growth is again restricted at lower triaxicity. However, when we go to the higher triaxicity, the growth is continuous and the void keeps growing. So this restricting void growth is not observed at higher triaxicity. Now a slightly bigger void, the second size. Now here again the behavior remains same. The only thing you should look at these values with the increasing strain rate, the higher and higher stresses are required, because your material is rate dependent. It response to the material is higher and higher. It requires higher and higher stress to resist more and more loading. So with the increasing strain rate, higher stresses are required, whereas the characteristics remain same. When we go for a smaller void, when we go for a slightly larger void, what we see, the behavior is still the same. However, the softening becomes more prominent. The softening just after the peak stress become more and more prominent. For a smaller void, these softening were absent in case of the higher triaxicity, whereas now the softening is even observed at a higher triaxicity. When we look at the largest void, which is having the highest radius, again the feature is same. The softening has become even more prominent, and now we can see the unstable void growth even in case of the highest triaxicity. Okay, so whereas again with respect to strain rate, the response remains same. It requires higher and higher stress. So now what I am interested in, this peak stress, which is basically causing the sudden void expansion, because that will basically determine when the void is expanding in an unstable manner, or at least sudden expansion. So I look at all the peak stresses, and this is the distribution, this is the variation of peak stress for different void sizes with respect to the loading rate. Here the log of loading rate has been plotted. Now what we see that these mean stresses vary up to a certain loading rate, and after that, so mean stress basically increases with the loading rate. And this is what has been observed, this is what was observed in the experiment, that the mean stresses required for void growth are higher at higher strain rates. So this is what we can characterize through these void growth simulations, that at higher loading rate, higher mean stresses are required for sudden void growth. Again, these are for three different void sizes. Now if we look at, so this is in a global sense, we are looking at the mean stress criteria. Now if we go into the physics of what is happening at the void growth, let us look at individual cases. So this is the lowest triaxicity uniaxial case, slowest loading rate, and smallest void. Okay. Now I look at the situation near the void, at different instances. So as I said that initial growth is almost linear, so this line shows a linear pattern. So up to this point void is growing almost elastically. That means if the unloading happens, the void will again come to its original state. That is also confirmed when you see the equivalent plastic shear strain at the first point. The plastic strain is very small, so it confirms that this growth is almost elastic. Now when we go to the second point, that is the peak of the main stress, what we see that there is a shear band which is almost at a 45-degree angle, which actually causes the plastic strain in the whole cell. With the increase in loading or with the increase in void size, the shear band actually keeps growing throughout the cell and the plastic strain starts developing throughout the cell. Now when the hardening starts coming into the picture, the plastic strain rate again decreases, and ultimately at 0.5 plastic strain rate is almost 0, or it is basically very small. So basically the whole cell is now expanding at a constant strain rate, and it actually expands like a unit cell or kind of a homogeneous plastic strain. That is what we can say when the void is smaller. Now we look at the same case, lowest reactivity is lowest loading rate, but a larger void. What happens? The same case, the similar is almost situation, but what happens now, because the ligament between the void and the boundary is small, now again here a 45-degree band is observed, but now the plastic strain is more or less distributed in throughout the cell. That is the only difference what we see when we go for the larger void. Now we look at the condition at highest reactivity. Okay, highest reactivity is lowest loading rate, is smallest void. Okay. Now here the situation, as soon as the reactivity becomes high, the situation completely changes. Again, this is the initial point where the elastic growth is there, no plastic strain rate. Now when the plastic strain rate starts developing, it is now very local. It is not spreading throughout the cell, it is very local near the void. So the whole plastic straining is happening only near the void. The plastic deformation is happening only near the void. With the increase in void, this shear strain rate starts increasing towards the x2 axis, and still it is still locally around the void. There is no shear bands following throughout the specimen. So this kind of transition from this 45-degree shear band to this kind of local plastic straining happens somewhere between the slowest reactivity to the highest reactivity, and it has been well discussed with in earlier work. Okay, I am not going to discuss that. So at slowest reactivity we see a shear bands going in 45-degree direction, whereas at higher reactivity we see this kind of local plastic deformations. Similar plastic deformation. So this is the larger void. In the larger void, again what we see the similar kind of local plastic deformation, but now what happens, because this ligament has become small, now this plastic deformations goes across the cell. Okay, because so you can imagine there is a cell along this also, because it's a periodic boundary condition. So now the whole ligament is under plastic deformation, and this plastic strain now grows as a shear band throughout this ligament, and ultimately this whole ligament actually stretches like, and it is under a uniaxial deformation. So this kind of so now you can see this has almost become a straight, and initially which was a circular shape, now it has almost become a straight, and this part is now expanding just like a uniaxial specimen. So when the fracture happens, it will probably happen here somewhere. Now if you look at the plastic strain in all these cases, that this is what we can see. This is the first case which we have seen, smallest void, the smallest void and the lowest reactivity, uniform plastic deformation. This we have already seen. This is the highest reactivity, again very localized plastic deformation near the void. This is the large void, everywhere there is a plastic strain, non-homogeneous, and this is the plastic strain only in the ligament, else there is no plastic strain. So this is the case when at the slowest loading. Okay. Now we go to the dynamic condition. So for the dynamic condition, maintaining a constant reactivity is a problem. So what we do, we only consider three cases where it is easy to maintain the constant reactivity. What are those three cases? Those three cases are uniaxial loading, equibiaxial loading and hydrostatic loading. In this case what we do, we maintain the, we restrict this edge to remain straight and apply the loading in this direction. So this is like a uniaxial loading periodic boundary condition. This is the second case where we apply the loading in radial direction. Because it's an axisymmetric case, when you are applying the loading here, it means that you are applying the loading in every direction. So this is like a biaxial loading. This edge is maintained to remain straight, so that it is a periodic boundary condition, and then we have the hydrostatic loading, where the loading is same in both the directions. So these are the three conditions which are easy to apply in case of the dynamic conditions. Okay, and at all other nodes we apply initial boundary conditions, so that we can avoid the higher distortion at the initial time stage because of the stress waves. Now, if you compare these results, with the static results, so static simulations. So basically, these are four figures: the two lines and the two dotted lines. What are these results? So the two dots, orange and yellow, they are basically the results from static simulations where the inertia was off. The two lines, dotted and continuous, they are the same simulations at the same strain rates, but the inertia is on. Okay, so what we see there at all triaxiality, what we see that up to a strain rate of 10 power 3 per second, we don't see any difference between the static response and the dynamic response. What does it say? It says that the inertia has not become significant till a strain rate of 10 power 3 second per second. Okay. However, you can see at a strain rate of 10 power 3 second, you can start seeing some wiggles here, which basically shows that the inertia has started coming into picture, and it shows some wiggles in all the cases. Okay. So we can say that 10 power 3 per second is kind of a boundary where the inertia will start coming into the picture. Okay, this is for one void. I am representing the results. For rest of the voids also the similar kind of situations are observed. Now, if I look at higher strain rate, so these are the strain rates up to which we don't see any inertia effect. So now we go to a higher strain rate where E dot is equal to 10 power 5 per second. What we see here, again for some void size, what we see that the inertia effects are now becoming significant. So this is a response for uniaxial loading under under uniaxial loading static simulation, that is inertia was off, and this is the response when the inertia is on under the same uniaxial loading. You can see the difference between the static response and the dynamic response. The whole difference is coming only because of inertia, because material rate dependence is already included in this part. Okay, what you can see, the inertia is actually making it difficult for void to grow. It is even making it difficult to grow in the elastic region. In this case, you can see a slope, elastic slope, whereas here you can see the elastic slope is very steep. That means even in the case of elastic growth, the void growth becomes difficult because of the inertia effect. Okay. The same thing you can observe at higher triaxiality, the difference is even higher. This is the biaxial loading static case, this is a biaxial loading dynamic case. You can see the difference is even higher in this case. That means with the increase in triaxiality, the inertia effects are also becoming increasing, they are also becoming large. Okay. So this is what we observe here. Now, if you look at the mechanism of void growth, so here if you see here up to 10 power 3 per second, whether you do a static simulations or dynamic simulation, the void growth phenomena does not change, the void growth shape does not change. Whether it is dynamic condition, static simulation, the most of the mechanism remains same. But since here inertia effects are being introduced, the void growth mechanism will not remain same. So that can be confirmed by looking at the void growth profile. Now here what I am showing is the void growth profile at constant f dot. For example, for 1 by 3 I am looking at the void growth at these 2 points, void growth at these 2 points. So this black line shows the initial shape of the void, whereas the blue line and the orange line shows the void growth at two successive instances. Now if you see here, when inertia is not present, void is growing almost in a prolet manner. It makes it kind of a prolet spheroidal. Whereas when the inertia is present, it actually tries to expand it in a more spheroidal like manner compared to what is there in a prolet like manner. That means inertia, it is because inertia is acting in every direction. So basically this growth is more towards like a higher triaxiatic case. When we apply a hydrostatic kind of loading, this is how the void tries to grow symmetrically in every direction. So even though the triaxiality is less here, the void is growing in a manner the way it will grow in a high triaxiality loading condition. This is for a biaxial case. Here, instead of becoming prolate, it is now becoming an oblate kind of, it is now growing in an oblate kind of manner. Initially this was like this, then the blue line, then it is like orange line. Whereas again, if you see here, it again tries to expand in a more symmetrical manner, more spherical like manner. So this is what is the effect of inertia, which is trying to bring void in a, it is trying to expand the void in a more spheroidal like manner. Now this is at the highest triaxiality, which is at the which is kind of a hydrostatic loading. Okay, E dot highest triaxiality, highest loading rate. Here you can see I have plotted it for different void sizes. Now these are the three static cases for smallest void, medium void, largest void. This is what we have seen earlier. These are the three dynamic cases for again for smallest void, larger void and the largest void. What we can see here, that inertia effects are also amplifying with triaxiality. We have already seen inertia effects amplifying with triaxiality. Here we can see inertia effects are also amplifying with the larger void size. The gap between the orange line, both the orange line, the gap between both the green lines and the gap between both the blue lines actually shows what is the contribution of inertia in growing these voids. So we can see that it is growing with the increasing void size also. So higher the void, difficult will be void to grow, okay, and because of the higher inertia at higher loading rates. So this is what is the overall effect of inertia on the void growth in these amorphous polymers. So in a summary, I can say the effect of material rate dependence on the inertia and inertia effect on the void growth are quantified at higher loading rates. Void growth mechanics remain unchanged in the absence of inertia. So mechanics does not change if inertia is not present. Inertia effects when become prominent, they stabilizes the void growth. So now if you can see here, earlier the void which was growing instably after the peak stress, now it has become very stable. Now the void growth has become difficult, it has also become stable. It is not growing in an unstable manner. So inertia is basically making the void stable. Inertia promotes a spheroidal like crack growth, the void growth at all triaxialities. So that's all. Acknowledge for the funding from the SERB DST. Thank you.
So thank you. Questions and comments or?
That transition where the inertia effects was coming, you have shown one particular value. Is this a case specific or it is?
Yeah, it is in this case this is the polymer specific, but because the for more or less all polymers the density will remain almost constant. I think this will be the kind of density you will see for all. This is the kind of standard you will see for all polymers.
Okay.
You should see.
Okay.
Okay.
In the first part of the talk, so you mentioned about this this strain rate dependence.
Right.
So there for this depression or some depression loading and impact loading, like why you didn't change the strain rate of the depression itself, because the geometry was little different, right?
Which case?
Yeah, this one. This
Yeah.
is like impact loading,
Right.
and previous one like it was.
Yeah, this is slow loading.
No, but you compared this case with that impact loading.
No, this is just to motivate why the void growth is important. So basically what we want to understand here is the voids are causing the failure, voids are kind of precursor to failure. Okay, so this is kind of that, but we actually compared these results, that the mean stresses which are required for defect growth or void growth is basically increases with loading rate.
So
this
these
is
are
what
these are all impact loading.
These are impact loading. This is slow loading. So you can see this is the rate.
Yeah.
So these are the impact loading. This is slow.
Yeah, I was wondering that slow loading, that if you keep the same geometry but make it faster and faster, can you like also compare that without like going from
same geometry,
but making like that loading rate faster and faster without impact is a different, I think, like it is something is coming and hitting probably.
no, basically yeah, so basically that will lie somewhere here. That will lie somewhere here.
It will smoothly connect.
Yeah, so these kind of tests are yeah, that they are available, but you will see some kind of connecting between them. Most of the contribution comes from the inertia. That's why people look at generally these rates. But yeah, you can up to a certain rate you will see this is constant. After that, picking it up.
Yeah, you need really high rates actually.
Yeah. So these rates are coming from the Hopkinson bar kind of setups.
Other questions, comments? Well, I have one. I'm just thinking of an old demonstration. You take a plastic bag. So here's where you hold it, and it's been stretched in this way. This is the production direction. So if you cut the strip in this way and this way, if you pull on this strip, then you get this work hardening. You see exactly what you see here. But if you take it the other way, it breaks almost immediately. And that is simply because the polymers have a sort of a direction, so that when you push like this, you see this picture. But if you pull in the other way, it breaks immediately. Yeah. What would that look like in your framework?
That is probably the anisotropy of the polymer. The property is same. If it is isotropic, it should be same in all the directions. The behavior should be same in all directions. Yeah, for example, if I take a polycarbonate sheet, if I cut two specimen in two perpendicular direction, I should get the similar kind of behavior.
Yeah, but that's because it's been produced in such a way that it doesn't have any preferred direction. But plastic bags are very anisotropic.
Yeah. So. So there are two kinds of there are two ways in which a polymer fails. One is basically because of the shear yielding, in which it undergoes a large deformation and fails. Another way it fails is basically the crazing. So crazing is the phenomena where the crazes appears in the ahead of the crack. I don't have a picture. Yeah. So basically the crazes are so if there is a crack, then ahead of the crack, somewhere ahead of the crack, there is a damage zone, and it will basically form some kind of breezes here.
Yeah.
So this is called crazing. So if crazing has come into the, so if you have ever looked at old plastic bottles and all those things, you will see, if you will see in the light, you can see small cracks. Still it has not broken. So those are the crazes which has come, and if the crazes have come in the polymer, it will fail in a brittle manner. So probably that is what is happening when we pull it in the other direction.
Yeah. And then I have another question also, and that pertains to the picture of the slide you showed when you answered your question. Because you see, when you have the notch and you open it up, you see this tongue that sort of comes out, and it always comes from the center line, the symmetric line.
Yes.
Yeah.
In this case. Yeah.
And yes, and you know, I would have thought, perhaps with a certain lack of intuition, that it should start from the corners, because that's where you get the largest stresses. But clearly, it starts in the middle.
No, the middle section is the weaker section. Right? It is ahead of the notch. There, the stresses are high.
Yeah. So it's not the corners, because usually it's corners.
Oh, you mean along the thickness?
If you take the picture before.
Along the thickness, you mean?
Yeah. If you go to the picture before, perhaps the other way. Perhaps the other way.
Oh, okay. Yeah, right. This is faster.
That one, yes.
Yeah. So
I mean,
in fact,
you see, it starts in the middle.
Yeah,
And
in
it
fact,
grows
this is
out.
also
Why
at the
doesn't it start
center.
in
In fact,
the two
this is
corners
also
and go
coming
in?
at the center, somewhere in the
Yeah.
center,
Yeah.
because in between there is a plane stress condition and the triaxidity is higher in between.
Yeah.
So that is where the chances of growing is higher. That's why it comes at the center. Because towards the surface it's a plane stress condition. The stresses are zero at the surfaces, whereas inside the material there are stresses in every direction. So it is easy to grow at the center compared to at the surface.
Yeah. Okay. Thank you. Other questions or comments or whatever? Nope. Well, thank you again.
Thank you.